Hello and welcome. I'm Dr. Syed Mostafa Safavi, and you're listening to our podcast series on deep learning for intrusion detection. In this series, we explore how cutting-edge AI techniques are reshaping the way we detect and respond to cybersecurity threats. This podcast is produced with the valuable support of Alicia Tan, who has been instrumental in coordinating and preparing each episode. Now, let's get started and dive into today's topic. Welcome to our podcast, diving into the fascinating world of network intrusion detection and deep learning techniques, with a special focus on datasets, protocols, and even PE files analysis.
I'm really excited about this discussion. There's so much to explore, especially when it comes to tagging patterns in network traffic and the overall architecture behind IDS systems.
Exactly. So, one of the core points here is that intrusion detection isn't about looking at isolated instances like malware files, but rather it's about recognizing patterns of activity. Essentially, you build a predictive model, a classifier, to distinguish between good, normal connections and those bad connections or attacks.
Right, so it's a bit like trying to figure out a hidden pattern in a massive maze of data, isn't it?
Yeah. It's like you're trying to see the forest for the trees, And for that, you need robust datasets, which, for example, we see in the KDD99 dataset. It lays out connections with detailed features, like duration, protocol, bytes transferred, and so on.
And the KDD99 dataset also dives into derived features, right? Like same host or same service features that look at patterns over time, not just a single packet.
Totally. It's quite ingenious. For instance, by using a 2-second time window, you capture the immediate behavior of connections, while also having host-based features that might span, say, 100 connections to the same host. This multi-layered approach helps in discerning subtle anomalies from genuine traffic.
But isn't there a challenge in dealing with, say, R2L and U2R attacks, since they are often embedded within the data of a single connection?
Absolutely, and that's a really good point. Typically, these kinds of attacks don't show sequential patterns because they often occur in just one connection. So, additional content features like failed login attempts, hot indicators, or even checking if a root shell was obtained, become crucial.
That makes complete sense. Shifting gears a little, can we talk about how this plays out in the machine learning context, especially regarding deep learning for intrusion detection?
For sure. The idea is to leverage machine learning, say, using a random forest algorithm to classify connections. They extract about 191 features from each connection. But we then reduce the dimensionality with fast correlation-based feature selection, which whittles it down to about 55 essential non-redundant features.
Right, that sounds efficient. It's interesting because reducing dimensionality not only boosts performance, but also helps in minimizing overfitting, especially when working with network data, which can be quite noisy.
Indeed, that's true. And with the random forest, they adjusted parameters like the number of trees, around 2,000 trees, using information gain, and set minimum samples at leaf nodes, as well as for splitting.
Yep, parameters are critical for fine-tuning performance. I do wonder, though, why those specific thresholds? I mean, wouldn't a slightly different configuration potentially lead to lower false positive rates?
That's a valid critique. In fact, they used receiver operating characteristic, or ROC analysis, to nail down the optimal threshold for the percentage of voting trees. The idea was to balance a high true positive rate with a very low false positive rate. Ideally, no more than 5 false positives per period.
Yeah, I can see that. So if I'm understanding correctly, they found that having at least 85% of the trees vote for malicious meant a TPR of 0.706 and an FPR of 0.001, which seems like a solid trade-off for their system size.
Exactly. It's like setting a security checkpoint where enough of the analyzers have to agree before declaring something malicious. But interestingly, there was a note that they might have chosen the wrong emphasis in some cases. Minimizing FPR is generally more crucial for authentication, while minimizing FNR is important for detecting malicious activity.
That's a nuanced but important distinction. Now, moving on to another key area, can we touch on the structure of the Internet protocols discussed here, like encapsulation, Ethernet, IP, and TCP?
Sure thing. At the basic level, the entire idea of encapsulation is that a packet is a structured message. Each layer of the network stack only deals with its specific header information. The Ethernet layer, for example, deals with MAC addresses, while IP takes care of routing, and then TCP handles the segmentation and reliability aspects.
True that. So, each layer gets the relevant data for processing, and then as the packet moves through the layers, headers get added and later stripped off, ensuring that every protocol only interacts with its own prescribed data.
Exactly, it's like a well-organized postal service.
Right.
Each layer being independent prevents data from getting mixed up and ensures proper delivery of information.
Speaking of delivery, what about IDS systems like Snort? I noticed a deep dive into Snort's rule-based system in the content.
Yes, Snort is quite interesting. It's an open-source network IDS that performs real-time traffic analysis and packet logging on IP networks. It uses a rule-based language that can detect various attacks, from buffer overflows to stealth port scans, and it's flexible enough to perform protocol analysis, content searching, and even taking action on the results.
That's powerful. And those Snort rules are divided into the header and the options, right? Where you specify the packet attributes and then what to inspect in the payload.
Exactly. The rule header indicates who, where, and what the packet's about, like the source, destination, and protocol, while the rule options delve into the specifics, such as looking for a particular hex sequence in the payload.
Yeah, that's like having a filter that only flags packets matching very specific criteria. And then there's the dynamic rule pairs for tracking exploits. It's like linking together a sequence of suspicious packets.
Right. Those activate dynamic rule pairs are designed to catch multi-packet exploits. They ensure that if an initial suspicious action is detected, subsequent related actions are monitored, effectively piecing together the attack narrative.
Really clever. Now let's bring the conversation back to PE files. The content covers portable executable files in detail.
Yes, indeed. PE files, which are basically Windows binaries like exe and DLL files, have a very well-defined structure. They start with an MS-DOS header and then include various sections such as .text for code, .data for variables, and .des for uninitialized data.
Yep, and that structure can reveal a lot about whether a file is malicious, right? Because malicious PE files often employ evasion techniques like packing or obfuscation. So, by analyzing section names, order, entropy values, and even suspicious imports, you can detect potentially dangerous files.
Exactly. For instance, if a section's entropy is above 6.7, that might indicate the file is packed, a common sign of evasion. And using tools like the pfile Python library, you can extract and analyze these features quite systematically.
It's like detective work on steroids, and then they feed these extracted features into a machine learning model, similar to what was done with the network intrusion detection, right?
Yes, exactly. They extracted around 191 features from each PE, used FCBF to reduce them to 55, and then applied a random forest algorithm for classification. It's really fascinating how these techniques converge from different domains: network security and file analysis.
Absolutely. It's an impressive integration of traditional security analysis and modern machine learning techniques. I have to say, though, one might critique that while the process seems thorough, the reliance on static analysis might miss some dynamic behaviors, right?
That's an excellent observation. Static analysis gives a great first look, but indeed dynamic analysis, like monitoring the behavior of a PE file when executed, could complement it. It's a trade-off between speed and thoroughness.
Exactly. And what about the production system they outline? It appears that once a file is flagged as malicious, an analyst is involved to verify the alert.
Correct. The production system is designed to automatically classify and, if needed, generate alerts for malicious PE files. But then a human analyst steps in to confirm and handle the file, so it's a semi-automated pipeline. It's a smart way to keep the system adaptive, adding confirmed malicious signs back into the training dataset.
Right, a feedback loop to continuously improve the classifier. Speaking of feedback loops, did you notice the neat integration of ROC analysis? It really underscores the importance of selecting the right threshold.
Absolutely. Using ROC to find that sweet spot, where say 85% of the random forest trees voting malicious yields a TPR of 70.6% and an FPR of 0.1%, is crucial. It shows how statistical analysis can inform real-world thresholds in security systems.
That's the kind of data-driven insight we need in cybersecurity. In wrapping up, it's clear that the interplay of detailed protocol understanding, rule-based intrusion detection via systems like Snort, and modern machine learning techniques creates a powerful toolkit for cybersecurity.
Exactly. It's like a multi-layered defense system. One layer inspects network packets, another digs deep into file structures, and machine learning ties the whole thing together with predictive analytics. It truly is a comprehensive approach to, defending systems from intrusion.
It really is. Thanks for such an insightful discussion. The convergence of deep learning, static analysis, and classic IDS mechanisms really highlights the evolving nature of cybersecurity.
Thanks for listening, and I hope you feel as motivated as I do to continue exploring these innovative solutions in network and file security. Until next time.